Question 3, part B. So again, S is the unit sphere inside R3. Let F be a continuous function from S to R. Show that there must exist a pair of diametrically opposite points on S at which F assumes the same value. So what it's asking is that to find x and negative x inside S such that f of x is equal to f of negative x. Show that this must happen at least once. So your instructor gave me a hint, and his hint was to consider a function. Consider a function g defined like this. So now it is equivalent to ask find x inside S such that g of x is equal to 0. Because if g of x is equal to 0, then this is satisfied trivially. And this is trivial, least satisfied. So the goal of our question will instead be to find some instance such that g of x is 0. So let's pick x naught inside S arbitrarily. Case 1, because I like working in cases. G of x naught is equal to 0. Then I'm already done. Case 2, g of x naught is not equal to 0. This is the case that requires some work. So without a loss of generality, g of x will be positive, right? It's either positive or negative. I pick positive. We observe that this function g that we have in front of us is an odd function. So what do I mean by that? G of negative x is equal to f of negative x subtract f of minus x. And if you simplify that, that's negative of fx subtract f of negative x. And that's just negative gx. And this is true for all x inside S. So in other words, g is an odd function. More specifically, since g of x naught is positive, then it stands to reason that g of negative x naught is negative. So if I were to draw a sphere, okay, I would have a point x naught, and I have a point negative x naught, because they're diametrically opposite. I would have that g of x naught is greater than 0, and I have g of negative x naught is less than 0. And by question 3a, there would be a path that goes from x naught to negative x, because S is path connected. But that's just question 3a. And this path doesn't go through the origin, or none of the paths go through the origin. This path is on the surface of S. That's what I mean to say. So on this path, at this point here, at this point there, my value is greater than 0. And I keep going along the path, which is a continuous function, and so is g. And eventually get down here, suddenly I'm negative. So it stands to reason that at some point along the way on this path, let's say around here, I went from positive to 0 and then to negative. Because this is just a continuous, these are just continuous functions we're working with. So let's actually write down the proper details of what's going on. So S is path connected by question 3a. So let P be a path from x naught to negative x naught. Okay. If I were to take P and G and compose them, what do I get? I get that this is a continuous function. Such that G compose P of at 0, that's just G of x naught, which is greater than 0. And then I have G compose P at 1, that's just G of negative x naught, and I already said before that's less than 0. So the function of the interval 0, 1, at 0 I'm above, when the domain is 0 I'm above 0, and when I'm at 1 in domain I'm less than 0. So eventually I had to have hit 0. So therefore, by the intermediate value theorem, there would exist a time t naught in 0, 1 such that G compose P at t naught is equal to 0. So if I allow, let's say, y to be equal to the point inside S when the path is at time t naught, if I consider that point, then G of y would be equal to 0. And as we said before, our goal is just to find an instance. Our goal is to find an instance such that G of x is equal to 0. And I've done that. So therefore I'm done. So question 3b is a really good question because it combines paths, it combines compact sets, it combines intermediate value theorem all together. So that's it for question 3b.